Hello guys, this is Code and Code, and this is an editorial for this problem, Fibonacci finding, taken from HackerRank. The problem is taken from HackerRank, and this problem is in continuation to the 7th lecture of the number theory series. So if you haven't seen that 7th lecture, just go and check out that lecture, and then if you know recurrence relation and matrix exponentiation, which I have explained previously, so you are good to go. Before starting the lecture, if you wanna help this channel grow financially, you can pay some donations, and the description of the donation payment is in the description. So now about the problem. So the problem is, you are given first and second term of a recurrence relation, and the nth term is defined as the sum of previous two terms. This is basically like Fibonacci series, but the terms doesn't start from 1 it starts from A and B. So you are given t test cases. In each test case you are given 3 terms A, B and N, and you have to print the nth term of this Fibonacci series. And we have to print, of course, the nth term modulo 10 to the power 9 plus 7, because the Fibonacci series grows exponentially. Now if we take a look at the sample test cases, t is 3. There are 3 test cases. The first series is this, starting from 2 and 5, and we have to print the first term. First means this is in the test case. In the problem it is taken 0 base index. The indices are 0 base, so we have to print actually the second term. Here we have to print the third term, and here we have to print the fourth term. So if you take the starting 2 elements, these 2 and 5, the series would look something like this: 7 and then 12 and then 19, so goes for this and this. So we have to print the index 1 element, which is basically second element. So what I'll be doing, I'll simply increment it. I'll doing it n plus plus, so I'll printing second term, which is 5. Answer of this is third term, which is 9. Answer of this is the fourth term, which is 17. So we won't be working with the 0 base in system. We would be working with 1 base system. All you have to do is simply increment this. So as you already know, in the matrix exponentiation lecture, and after that we have studied how we can calculate the nth term of a recurrence relation using matrix exponentiation. So you know that, okay, we can calculate this, the nth term, in log n time. So the first thing using matrix exponentiation is to find the transition matrix. So if you have taken that lecture, you might be familiar with this expression. What this is a row matrix of base cases or base terms. Base terms are f1 and f2, the first two terms, because first two terms are given and we have to print the nth term. If you multiply it with the transition matrix, the result is f2, f3, that is the next terms. All this I have explained previously, so I am not going into the details. So the purpose is to find this, the transition matrix. So we know f2 and f3 are f1p plus f2r if we multiply these two matrices, and f3 is equals to f1q plus f2s. If you solve these two equations, you will find p is 0 and r is 1. If you replace p with 0 and r with 1, the left hand side and the right hand side becomes equal or equate. And for the second equation, if you take q and s to be 1 1, so f3 is sum of previous two terms, and that is why q and s would be 1. So the transition matrix would be 0 1 1 1. After we have find the transition matrix, all we have to do to find the nth term, first, if n is 1 or 2, we can simply return these two terms. I mean, if n is 1, we will return f1. If n is 2, we will return f2, of course. If n is greater than that, what we would do, we would take the transition matrix, calculate its power n minus 1, and then multiply these two and return the first term, because first term would be the nth term of that Fibonacci series. Again, this I have already explained in previous lecture, so I'm not going into the details. Now all we have to do is check if n is less than equals to 2. If yes, then we would return the nth term, that is either the first or the second term, which would be the base case, so we don't have to make any calculation. Otherwise we will calculate t, that is transition matrix raised to power n minus 1, and then return the first term of multiplication of these two. First term would be f1 multiplied by 1 1 plus f2 multiplied with 2 1 of transition matrix raised to power n minus 1, and that would be our fn, the nth term. So enough talk, let's just jump into the editor and code. So let me make this a little bigger so you can see properly. So what we are doing here, we are taking t, that's case, and n, the nth term that we have to print. So I've taken array of size 3 so that I have indices 1 and 2. So I'm reading a and b in first and second indices, and then I'm reading n. After that I'm incremented it, so it becomes one base indexing. Now getFib is a function that is here that will return the nth term of this Fibonacci series. So how we do, as I have already explained, if n is less than or equals to 2, simply return AR of n. If n is 1, it would be 1. If n is 2, we would return second term. Otherwise, if you remember from matrix exponentiation lecture, first we would define the identity matrix, and you know, since the matrices are going to be of size 2 cross 2, so we can simply write here, I've taken the identity matrix and this is the transition matrix, all of size 3 cross 3, because I want indices from 1 to 2. So in identity matrix, element 1 1 and element 2 2 would be 1, and the rest would be 0, that is element 1 2 and element 2 1. After identity matrix, we have to define the transition matrix. Now transition matrix, you can see, is 0 1 1 1. So 0 1 1 1, so 1 1 element is 0, while the rest element of transition matrix, which are this 1 2 and 2 1 and 2 2, all the elements are 1. After doing this, we have to calculate the transition matrix raised to power n minus 1. So let's replace n with n minus 1, and this is the power we have to calculate. So if you remember from matrix exponentiation, we do while n, that is while n is greater than 0. If n is odd, that what we do I is equals to I into t and n minus minus. If you remember, we do this, right? So to do I is equals to I into t, we had defined multiplication function which takes 2 arguments, and yes, their dimension is 2, so I'll simply return pass 2 and then n minus minus. Else what we do t is equals to t into t, that is multiply t with t itself, and dimension are 2, and n would be n is equals to n by 2, right? So if you remember, this is nothing but the code that I have explained in matrix exponentiation. So if n is odd, what we are going to do, we are going to calculate I is equals to I into t. Otherwise we are going to calculate t is equals to t into t, and we would replace n with n by 2. So now it is important to write down this MUL, that is multiplication function, which takes 2 arrays, multiplies them, and save the result back into A. So to calculate that, yeah, LLI is long int I have defined here. LLI is basically long int, because the elements are of order 10 to the power 9, so their multiplication can go out of bound of integers. So I'm taking long int, which can take as large as, I guess, 10 to the power 19. So that is why result of size dimension plus 1, so it would be 3 cross 3. Now if you remember, the matrix multiplication algorithm, it is n cube. You run a loop I from 1 to dimension, then you run a loop j from 1 to dimension, and then result of ij is equals to 0, and then you run a loop k from 1 to n, that is dimension, and then k plus plus result of what we would do, we would like to do this plus equals multiplication of a ik multiplied with b kj. Now the problem here is that we have to calculate it modulo transfer 9 plus 7, because this may of course go out of bound of integer integer or even long int, because Fibonacci numbers grows exponentially. So if we'll do directly this, then it is likely to go integer of overflow. So instead of writing this, we do LLIX is equals to, since in the result we have to add this, so what we will do, we'll take this and take it modulo already, and MOD is actually transfer 9 plus 7. So first we would calculate these two and take their modulo, and then result of ij is, since we have to add it into result of ij, so result of ij is equals to result of ij plus x, and then take their modulo. So this way we can handle modulo part. After calculating it, of course, instead of running that loop, I'll simply run this loop. This looks better to me. We will copy all the values from result to back into array A. Again, this I have explained in previous lecture, so I'm not going to explain. So what we do, we would calculate A into B, which have dimension dim, and then we would save the result back into array A. So array A would get updated. So this array each time would get updated. So it would become I is equals to I into T, and it would become T is equals to T into T. And after doing that, what we have to do, we have T raised to power n saved in I. Basically, I contains the result now. I contains T raised to power n minus 1. And after we have calculated T raised to power n minus 1, all we have to do, we have to take the first element, multiply it with I11 plus second element I21, and then that would be the nth term. So to do that, x is equals to AR of 1, that is f first term, multiplied with result 11 plus second term multiplied with T raised to power n minus 1, this. So I contains T raised to power n minus 1. I is basically your result, which contains T raised to power n minus 1. To calculate the nth term, all we have to do, take f1 multiplied with I11 and f2 multiplied with I21, and then add both of them, and this would become the nth term, or basically you can write it as fn, and then we have to return the fn. This should work. I'm not always sure. Most of the time I just compile and get bunch of errors. I hope, yeah, this doesn't look very good, but this is the question from HackerRank Fibonacci finding, and these are the test cases. So let's run the test cases one by one. There are 8 test cases. First test case is 2 3 1 3. The answer is 3, which is here. Let me make it a little bigger. So here's the test case, and here's the answer. 2 3 1 answer is 3. 2 3 1 answer is 3. Let's take the 4th test case, which is giving us answer 178, and 4 test cases 2 4 9. So 2 4 9 is giving result 178. So everything is going good. Just let's simply take our code and paste it. in here. Let's run it. So it is processing. Come on, boy. And yep, sample test case passes. So let's submit it. And yeah, congrats, we have solved this problem. So I hope you have understood it, that how you can solve a problem related to recurrence relation using matrix exponentiation. If you had no idea about the matrix exponentiation, solving this problem would have been too hard, believe me, because n can be as large as 10 to the power 9 and there are 10 to the power 3 test cases. So it would have been too hard to solve us without matrix exponentiation. So I hope you guys have understood something from it and you will try this yourself. There is one more problem which is much difficult than this one, because it only depends on previous two terms, and each time it would of course depend upon previous two terms. But on spot there is a problem in which there are t test cases, and in each test case the nth term depends upon previous k terms, and k can be as large as 10, and in each test case k can be different. So we have to dynamically define this transition matrix. Here what we can do, we can actually define transition matrix once, and for every test case transition matrix would be same. But there what would happen, the transition matrix would not be same. That would be changing depending about the test case. So that is a bit difficult, more difficult than this one. So in the next lecture we would be solving that problem, and I hope you guys have learned something from it. And if you guys think that the work that I do is appreciable and you want to of course support it financially, you can go and donate whatever you can. So again, the details are in description. So thank you guys for watching. Until next video, keep coding. Thank you and bye.